Hello. By now you know that the college is going to be closed Thursday, Friday, and Saturday, and we're going to be doing online classes in the future. I want to catch you up with this video on what's left of the discussion about trees. First, we're going to talk about binary expression trees. A binary expression tree basically is like a binary tree, except that each leaf node contains a single operand, like the doubles or integers, and each non-leaf node contains an operator, like a plus or minus. Here's a very simple example of a binary expression tree. And the in-order traversal gives us the normal algebraic expression 8 minus 5. So the levels in a binary expression tree indicate the level of precedence. Higher levels are evaluated later than those below them. And so what I recommend when you do an in-order traversal, the in-order traversal will present the expression tree as an algebraic expression, but I suggest that you put parentheses around the subtrees, each subtree. So 4 plus 2 has an parentheses around it, and then 4 plus 2 quantity times 3 has a parentheses around it as well. So the NLR and RLRN expressions, the prefix and postfix expressions, are similar. They're just the same. They evaluate to the same thing. The LNR, the in-order traversal, evaluates to 4 plus 2 is 6 times 3 is 18. Actually, the prefix and postfix evaluate to the same thing, but it's easier for us, of course, to do the algebraic expression. So here are the three expressions, the three traversals of the tree. Notice the 4 plus 2 has parentheses around it. That's because it's a subtree, and we want to make sure that we think of this in terms of putting parentheses around it. So a binary search tree in the linked implementation, if it's balanced, has an order log n order of complexity. The problem with a linked implementation is that when it's not balanced, and in fact this is true of any kind of representation, when it's not balanced, it's highly skewed. And so we'll talk a little bit about balancing a binary search tree. So binary search tree linked implementation, the basic node looks like this, with the left child and the right child pointers, as we talked about last time. The number of bytes in the node is critical to understand how slow it goes. So one of the keys to keeping a binary search tree running at order log n is to rebalance them whenever they get out of balance. There are two implementations that we talk about. These two implementations are not critical for you to understand, but you do need to know the nomenclature. So there's an AVL tree and there's a RedBlack tree. They're both rebalancing operations. The AVL tree was named after Adelson, Velsky, and Landis from the 60s. And the idea is to keep the insert and delete algorithms expanded to keep the height of the roots left and right subtree within one of each other. So we need to expand the insert algorithm and the delete algorithm, but not the fetch and update. Here's some examples of some AVL trees and a couple non-AVL trees. This is not an AVL tree because the depth of one branch is greater than of the other. So once again, you're not responsible for this discussion, but the balance factor, you do need to know about rebalancing and rotating. You need to know the word rotating. So here is an example where the balance factor is kept alongside each node. For example, on the far left, you have the node 50, the key 50, and the balance factor is kept as 0 because it's the only node in the tree. Then when the node 63 is added to the right, 63's node has a balance factor of 0, but 50 has a balance factor of -1. So you maintain that. The idea of an AVL tree is to maintain that that pointer or that integer to keep the balance factor and then reorganize it when it happens. So if we want to rebalance a tree, suppose we inserted 98 in this 2-element tree, and so now we have 3 elements. The 50, the root, has a -2 as the balance factor, and so that's out of bounds. We need to reorganize that. So here's a situation where we want to delete node 35, and we don't change anything, so we don't rebalance at all here. So a word you need to remember is the rotation. Not that you need to know how to rotate, but the fact that rotations happen. And that's what happens when the AVL tree gets out of balance. So if you insert 33 into this tree, you see that it's out of balance because the node 50, the root, has a balance factor of 2. And so you require a right rotation. Now this is not trivial because if you rotate it once to the right, 40 would be the root and it would have 3 children, but that's not allowed in a binary tree. So the first step is to rotate once, and we see that 47 does not have a parent, so we need to attach it to the left node of node 50. So here's some more examples of rotations. Sometimes 2 rotations are required. And in this case, when we add 44, we'll need to rotate twice. So once again, you don't need to know the details of an AVL tree or of a RedBlack tree. But here's the second type of tree that keeps balance correctly, and that's called a RedBlack tree. Again, it's not perfectly balanced when you first insert things, but you need to rotate so it balances using rotations. And you only need to add balancing to the insert and delete algorithms. There have to be 5 conditions that are contained in order for it to be a RedBlack tree. Here are the 5. Every node in the tree has to be red or black. The root is always black. The red node's children have to be black. And every path from a node to a null link, which is a leaf's left or right null reference, has to contain the same number of black nodes. And the tree has to be a binary search tree. So this was done a little bit later than an AVL tree in the 70s, and the developers figured out how to be slightly faster than an AVL tree. So off to the left, is an example, very small print, of a red-black tree. And notice how some of the nodes, 14 is black and 11, its root is black, but that's not prohibited by the rules. Only the fact that you have a red followed by a black. So you have to rotate a red-black tree as well, just like an AVL tree. You have to readjust the color changes when you've done that. And if you'd like, here's an example of a red-black tree that from online. So that's rebalancing. If you would like to look at the slides, the Carano slides about rebalancing, you're welcome to do so, although it's not, once again, we're not going to ask questions about rebalancing of AVL trees or of red-black trees.